Hello students, welcome. Previously on our KCSE 2025 chemistry predictions, we have done part 1 of chemistry PP1 in the first series. So we have done from question number 1 all the way to question number 15. So today we are going to proceed to part 2 of our series 1, where we are going to do question number 16 all the way to question number 31. Kindly stay with us until the end of the video. So we are going to start with question number 16, part A. We are told define the term relative atomic mass. And we are saying relative atomic mass, or RAM, is the average mass of an element compared to 1 out of 12 of the mass of carbon-12. That's the definition of the term relative atomic mass. But B, we are told element T consists of 2 isotopes, T62 and T64, in the ratio 7:3 respectively. We are told calculate the relative atomic mass of element T. We are having 2 marks. So when we want to calculate RM, we are having different formulas. So here we are having mass number 1 as 62. We are having mass number 1 times. Here we are given ratio abundance, not percentage abundance. So we are going to say times ratio number 1 plus we are going to have mass number 2, which they have given us 64, multiplied by ratio number 2. Then we divide all this by the total ratio, which we can get it by ratio 1 plus ratio 2. So in case they could have given us a percentage abundance instead of ratios, the formula will be mass number 1 times percentage number 1 plus mass number 2 times percentage number 2 divided by 100, because the total percentage is 100. So thereafter, we are supposed to put our values here. We are going to say 62, which is for the mass number 1, times 7 plus mass number 2, which is 64, times ratio number 2, which is 3, divided by the total ratio. That is ratio number 1, which is 7, plus 3, which we are going to get 10. When we put all this in the calculator, we are going to get 62.6. And remember, relative atomic mass has no unit. So learners, those are the answers for question number 16, part A, and also part B. We are going to proceed to question number 17. So in question number 17, we are told ethanol may be obtained from sugarcane and converted to ethene as shown below. So we are having here sugarcane, step 1, it is converted to ethanol, and we are having here step 2, ethanol is converted to ethene. So part A, we are told give the name of the process that take place in step 1. Step 1 is here. We are having sugarcane being converted to ethanol. So this process is fermentation process. And fermentation is the decomposition of organic substance like sugarcane or sugar into ethanol or alcohol, carbon dioxide, and also heat by microorganisms. Okay, part B, we are told name the type of reagent and condition in step 2. So step 2 is here. We are having ethanol being converted to ethene. So we can check here by just knowing the chemical properties of ethanol. One of them was dehydration of ethanol, because ethanol acts as a dehydrating agent. So to produce ethene, there we require dehydrating agent like concentrated sulfuric acid. So our reagent here is concentrated sulfuric acid. We can also use aluminum oxide. What is the condition for that dehydration process? The condition there is we are supposed to have temperature of between 160 degrees Celsius to 180 degrees Celsius. But when we're stating temperature, we have to be specific. So we can say temperature of 180 degrees Celsius instead of us giving a range. So learners, those are the answers for question number 17, part A, and also part B. So next, let's proceed to question number 18. We are told sulfur molecule has a higher melting point than phosphorus 5 chloride. Explain the difference in terms of structure and bonding. First of all, let's know that both sulfur molecules and also phosphorus 5 chlorides are molecular substances. So that means all of them, they're having covalent bond. But besides that, sulfur molecules exist in sulfate rings, sulfate bulkhead rings. But when we're talking about phosphorus 5 chloride, besides the covalent bonds, it has weak van der Waals forces. So that means they're having weak force of attraction when compared to sulfur molecules, because those ones, they're having strong covalent bonds. So question number 19, we are told give the name of the apparatus that can be used to prepare 2 molar sodium hydroxide solution in the laboratory. So our answer there is volumetric flask. So volumetric flask is the apparatus that's used to prepare standard solutions like 2 molar sodium hydroxide solution. So learners, let us see the answers for question number 18 and also number 19. So in number 18, we are saying a molecule of sulfur consists of bulkhead ring of sulfate atoms held together by stronger covalent bonds, while phosphorus 5 chloride exists as simple molecular substance with weak van der Waals force of attraction. So weak van der Waals forces are weak forces. For them to be broken down, they require less energy. So number 19, our answer is volumetric flask. So let's proceed to question number 20. So in question number 20, we are told determine the empirical formula of a compound containing the following: iron 28%, sulfur 24%, and the rest oxygen. And in bracket, we are given the relative atomic mass of iron, which is 56, the one for sulfur, which is 32, the one for oxygen, which is 16, 3 marks. So first of all, let's get the percentage composition of oxygen. How do we do that? First of all, we add the percentage of iron and that of sulfur. That's 28 plus 24. Here, we are going to get first of all 52. So if we want to get the percentage of oxygen, we are going to say 100 minus 52. So that means we are going to have 48% as the percentage composition of oxygen in this compound. So next, when we get the percentage of oxygen, we are going to write our element. Okay, we are going to write elements. The elements that we are talking about is iron, sulfur, and also oxygen. The number 2, we are going to write the symbols of those elements. Iron is written Fe, sulfur S, oxygen O. Then thereafter, we are going to write mass in form of percentage, or we can write percentage composition. So the percentage of iron is 28, the one for sulfur is 24, and the one for oxygen is 48. Thereafter, we get the Rm of the elements forming the compound. So iron is 56, sulfur is 32, then oxygen is 16. Thereafter, we are supposed to get the moles. How do we get moles? Mass divided by molar mass, or Rm. So our mass in percentage is 28 for iron. So we say 28 divided by 56. We are going to get 0.5 moles. Then the moles for sulfur, we are going to say 24 divided by 32. What we are going to get there is 0.75. Then down for oxygen, we are going to say 48 divided by 16, and we are going to get the 3. After that, we are supposed to get the mole ratio. The mole ratio, first of all, we are going to check the number of moles of each. Then we pick each moles, we divide by the smallest moles out of the 3. After that, we are going to write the empirical formula. So when we check our answer for question number 20, we are having our elements, iron, sulfur, and oxygen in symbol form. Then we are having the percentage composition, or our mass in percentage. We are having 28%, 24%, and also this 48%. We know how we have gotten that 48. Then the Rm is 56, 32, and 16. They have given us in the bracket. Then we proceed to moles. Moles is obtained by mass divided by Rm, or molar mass. We are going to get 0.5 in iron, 0.75 in sulfur, and 3 in oxygen side. Mole ratio. Here we are going to say 0.05, which is the number of moles for iron, divided by the smallest moles. The smallest 0.5 again. So we are going to have 1 there. Then 0.75, we have a 0.5, we are going to get 1.5. Here we are going to say 3 divided by 0.5, we are going to get 6. So check here, we are having 1.5. So we cannot round off this one to make it 2. Instead, we are going to make this one to be whole number by multiplying 2 in every side. So 1 times 2 will give us 2. Then 1.5 times 2 will give us 3. Then 6 times 2, we are going to get 12. So what will be the empirical formula? So it will be Fe2 S3O16. That's what we're going to have, the way you see here. But we can still simplify by putting Fe2 here, then sulfur and oxygen we put down there. Then what is the common factor there? The common factor there is 3. So we can put the 3 there. So we are having sulfur 3, then oxygen will be 4 inside, so that 4 times 3 will give us 12. So this formula here and what we have here are the same. So when we write in this way, we know we can write this formula. This is iron 3 sulfate. Iron 3 sulfate. So let's proceed to question number 21. In question number 21, part A, we are told draw a well-labeled diagram on how to prepare and collect wet hydrogen sulfide gas. So first of all, let's start with the reagents that we can use to prepare hydrogen sulfide gas. The formula is we are supposed to take any metal sulfide, like we can take iron 2 sulfide, we can take lead 2 sulfide. Then we react with any acid, like we can react with dilute hydrochloric acid. Then therefore, we are going to collect the gas of a warm water because hydrogen sulfide is soluble on cooled water. So part B, we are told describe the taste of hydrogen sulfide gas. So if you want to taste hydrogen sulfide gas, first of all, we are supposed to bubble or pass the gas into lead 2 acetate or lead 2 ethanoate vapor. Then it has to change to black due to the formation of lead 2 sulfide. Remember we said most metal sulfides are black in color, and they are also insoluble in water. So that's why we are seeing a black precipitate. So these are the answers for question number 21, part A, and also part B. In part A, check, we have used dilute hydrochloric acid in a dropping funnel. This is a dropping funnel. We are supposed to have the tap. Then we are having iron 2 sulfide as our solid there. We are having a delivery tube. Then we are collecting that hydrogen sulfide gas of our warm water because we said it is soluble in cooled water. So part B, to describe how to taste hydrogen sulfide gas, we bubbled the gas into lead 2 ethanoate or lead 2 acetate paper. Then it will change to black, and that's due to the formation of lead 2 sulfide. So next, let's proceed to question number 22, part A. We are told sodium metal reacts with air to form 2 oxides. Give the formula of the 2 oxides. We are going to have sodium oxide and sodium peroxide. So how do we write sodium oxide? Na2O. That's sodium oxide. What about sodium peroxide? We are going to write Na2O2 because we are told give the formula of the 2 oxides. So part B, we are told in the down cell, for the extraction of sodium metal, there is a possibility of producing liquid calcium at the cathode where sodium is also produced or formed. So we are asked, which 2 properties of calcium prevent it from mixing with sodium at the cathode? So number 1, we have to know first of all, calcium is denser than sodium. That's one property of calcium that prevents it from mixing with sodium. Number 2, calcium has a higher melting point than sodium. Those are the answers. So learners, these are the answers for question number 22, both part A and also part B. So next, question number 23, we are told below is a diagram showing how hydrogen can be prepared in the laboratory and its reactions with lead 2 oxide. So from the diagram we have here, we are told part A, name the reducing agents in the 2 reactions that take place in the setup above. So first of all, one reaction is here, that's the reaction between zinc and also hydrochloric acid. So here, zinc is a reducing agent. That's what you are supposed to know. Then the second reaction is here. First of all, the reaction between zinc and hydrochloric acid produces hydrogen gas, and that hydrogen gas will react with lead 2 oxide. So in that reaction, hydrogen is a reducing agent because it reduces lead 2 oxide to lead metal, and here liquid D will be water because hydrogen is oxidized to water. Okay, we are told part B, state and explain the observation made in the combustion tube. In the combustion tube, we are having first of all lead 2 oxide. That lead 2 oxide is yellow when cold, but we are heating here, it turns orange when hot. So we are going to have orange lead 2 oxide or orange solid changes to gray because lead metal is gray in color. So we're supposed to explain, and this is because hydrogen reduces orange lead 2 oxide to gray lead metal. That's the reason for that observation. So part C, we are to explain how the purity of liquid D can be determined. Remember, we said liquid D is water. So how can the purity of water be determined? By first of all heating it until it boils. Then we are told pure water boils at 100 degrees Celsius at sea level. Those are the answers for question number 23. So we are in question number 23. Answers. Part A, we're having zinc and also hydrogen. So part B, state and explain the observation made. We said orange solid turns to gray or changes to gray, and the reason is orange lead 2 oxide is reduced to gray lead metal by hydrogen. Then part C, to determine the purity of solid liquid D, we can say heat the liquid to its boiling point. Then we have to know pure water boils at 100 degrees Celsius at sea level and freezes at 0 degrees Celsius at sea level. So next, let's proceed to question number 24. We are told an element P has relative atomic mass of 88 when a current of 0.5 amperes was passed through a fused chloride of B for 32 minutes and 45 seconds. Full stop. We are told 0.44 gram of B were deposited at the cathode. So we are supposed to determine the charge on the ion of B. So in bracket, we are told 1 Faraday is equal to 96,500 coulombs. So first of all, if you want to calculate the charge, we are supposed to get first of all quantity of electricity passed, that is Q, and that Q is obtained by the formula IT, where I is the current in form of amperes and T is time, which must be in seconds. So this will be equal to, we are supposed to have 0.5 as our I because that's our current times time. The time here is 32 minutes. We have to multiply by 60 for us to convert it to seconds plus the 45 seconds that we have there. So here what we are going to get is 982.5 coulombs. That will be our quantity of electricity burst. Next, first of all, we are told get the charge. So that means we can say N, which is the number of Faradays, will be equal to Q, which we have gotten now, times the relative atomic mass, which we know that we are given 88, then we divide by M, which is the mass deposited in our case, 0.44 gram multiplied by F, that is Faraday, which we are given here as 96,500 coulombs. So when we put all those in the calculator, we are going to get 2.04 Faradays. So if we have 2.04, we have to make it whole number 2. That would be the charge. So when you're writing charge, we have to put plus 2. That will be our charge. So learners, those are the answers for question number 24. We proceed to question number 25. So in question number 5, we are told the apparatus below were used to determine the molar enthalpy of displacement of copper 2 ions. So this is the step that we are going to use here. We have plastic beaker, we have polystyrene cup, we have the thermometer there, and we're having here zinc with copper 2 sulfate solution. So part A, we are told explain why the polystyrene cup carrying the mixture of copper-2 sulfate and zinc was placed inside the plastic beaker. And the reason is, we are saying to minimize, or in order to minimize the heat loss from the system to the surrounding. That's the reason. So let's proceed to part B. We are told 1.0 gram of zinc powder was added to 100 centimeter cube of 0.2 molar copper-2 sulfate solution, and the mixture is stirred gently using a thermometer. We are told the temperature rose from 23 degrees Celsius to 30 degrees Celsius, and we are asked to determine the molar heat of displacement of copper-2 ions. In bracket, we are given Zn, which is the Rm of zinc, to be 65 to max. So first of all, we have to get the temperature change here. If you want to get the temperature change, we can use initial temperature minus final temperature. So here we are going to get 23 minus 30. So here we are going to get -7. So we write 7 degrees Celsius and we ignore the negative sign, even in calculation and even in writing here, because that negative is only telling us that this reaction is exothermic. So we are going to use it when we are writing the molar enthalpy. Okay, next. After that, we are going to get the enthalpy change. How are we going to get the enthalpy change? The formula for the enthalpy change is MC delta T, where M is mass, C is the specific heat capacity, and the temperature change we have gotten 7 here. The mass here is 100. We check it from the volume given. So we're going to say 100 times 4.2 for the specific heat capacity times 7 for the temperature change. Then we divide by 1000 for us to convert our answers into kilojoules. That 1000 is that we were converting 100 gram to kilogram, so that we get our answers in kilojoules. What we are going to get there will be -2.94 kilojoules after inserting those values. Next, we are going to get the number of moles of copper-2 ions and the number of moles of zinc. If they are the same, we pick one. If they are not the same, the number of moles, we pick the smaller moles. So let's start with the one for copper-2 sulfate. The way you see copper-2 sulfate, we are given 100 centimeter cube of 0.2 molar. So that means moles is obtained by molarity multiplied by volume used divided by 1000. There we are going to get 0.02 moles. But when we are talking about the one for zinc, here we are given the mass and we are given the Rm. So we are going to say 1.0 divided by 65.0. There we are going to get 0.0154 moles. So the two moles, the number of moles of zinc is less or smaller. So we are going to use that one as our number of moles. Then thereafter, how are we going to get the molar enthalpy of displacement? By taking the enthalpy change, then divided by the moles. There we are going to get 190.9 kilojoules per mole. So what's the sign? We have to put negative because there was a rise in temperature. So learners, these are the answers for question number 25, part A. We proceed to part B to see the calculation. So part B, we are told, first of all, we have to get the temperature change the way we have said. So 23 minus 30, we are going to get -7 degrees Celsius, but we are not going to show the negative sign. We are going to show the negative sign when we are writing the molar enthalpy of displacement. So next, we have to get the enthalpy change. The formula is MC delta T. We are having M as the mass of the solution, that is 100 gram times 4.2, which is the specific heat capacity times the temperature change. We are going to divide by 1000 so that we convert that 100 gram into kilograms, so that we get our answer in the enthalpy change as kilojoules. So the K is small letter, the J is capital letter. Next, moles of zinc, mass of Rm. We are going to get 0.0154 moles. Then we say this number of moles produces this amount of heat. What about 1 mole to get the molar enthalpy? So we're going to get 190.9 kilojoules per mole. So we're going to put the negative side because this reaction is exothermic because of the temperature has increased or temperature rose. In question number 26, we are told a student lowered a burning magnesium in a gas jar of carbon dioxide as shown in the diagram. So part A, we are told to state and explain the observations made in the gas jar. So here, magnesium is reacting with carbon dioxide. What we are going to get as our product is magnesium oxide and carbon. So what is the color of magnesium oxide? It's a white solid. What about carbon? Carbon is black sparks. So we're going to say a white solid and a black sparks are formed. So reason, this is because we are saying, first of all, the heat from burning magnesium decomposes carbon dioxide into carbon and oxygen. So the oxygen will react with magnesium, forming magnesium oxide, which is a white solid. So but B, we are told write the question for the reaction that is taking place in the gas there. So we are going to have there 2 moles of magnesium solid reacting with the carbon dioxide, which is a gas. What we are going to get there is 2 moles of magnesium oxide plus 1 mole of carbon. So this is the answer for question number 26, part A. Then we proceed to part B. So that's the answer for question number 26, part B. We proceed to question number 27. So in question number 27, we are told study the table below showing tests carried out on a sample of water and the results obtained. So we are having tests and also results. So the first test, addition of sodium hydroxide solution dropwise until in excess. We are going to see here white precipitate soluble in excess. So the inference there are 3 because we're having sodium hydroxide. So we're having there ZAP, zinc 2 ion, aluminum ion, and also lead 2 ion. Roman 2, addition of aqueous ammonia dropwise until in excess, colorless solution obtained. So that means here the ion is zinc 2 ions. Okay, Roman 3, addition of dilute hydrochloric acid followed by barium chloride solution. White precipitate is formed. So that is sulfide ions present. So part A, we are to identify the anion present in water. So that is sulfide ion. Sulfide ion. Then next we are having part B, write an equation for the reaction in step 3. So here we are having the barium ion in barium chloride aqueous reacting with the sulfide ions aqueous. What we are going to get is barium sulfate, which is the white precipitate, which is insoluble or which does not dissolve in the acid. So, but C, we are told write the formula of the complex ion formed in Roman 2 above. So in Roman 2, we are having addition of aqueous ammonia dropwise until in excess, and we are having a colorless solution obtained, and this was due to the formation of the complex ion called tetraamine zinc 2 ions. So how are we going to write tetraamine zinc 2 ions? We are going to write it like this. We are having zinc in bracket ammonia 4, then we close bracket. We are going to have 2 plus there. So these are the answers for question number 27, part A, part B, and also part C. We are going to proceed to question number 28. So in question number 28, part A, we are to explain why the ability of temporary hard water to conduct electricity falls when water is boiled, but it does not fall when temporary hardness is removed by addition of washing soda. Remember, washing soda is sodium carbonate. So the reason is that, first of all, the compound responsible for temporary hardness is the calcium hydrogen carbonate, and when heated, it decomposes to produce calcium carbonate, which is insoluble, hence lack mobile ions which will conduct electricity. But when we add washing soda, that's sodium carbonate, what we are going to get there is calcium carbonate and sodium hydrogen carbonate. So sodium hydrogen carbonate solution contains mobile ions which will conduct electricity. So but B, we are told the column below was used to soften hard water. We're having the hard water get into the resin or the column. We are having here the sodium permeate, then we are having here the soft water. So Roman 1, we are told after some time the material in the column is not able to soften hard water. How can the material be reactivated? So we say by flushing it with brine. And remember, brine is concentrated sodium chloride. Roman 2, explain how the hard water was softened as it passed through the column. Here we are saying the calcium ion or magnesium ion, which are responsible for the hardness of water, are exchanged with the sodium ions in the column, making the water soft. So these are the answers for question number 28, part A, and also question 28, part B. So we are going to proceed to question number 29. In question number 29, part A, we are told define the term radioactivity. And radioactivity is the process by which unstable nuclide breaks up to yield another nuclide of different composition with the emission of radiation in form of particles and energy. Part B, we are told give two differences between nuclear and chemical reactions. Number one, first of all, we talk about the location. We are going to say nuclear reactions takes place within the nucleus and involves protons and also neutrons. But when we're talking about chemical reactions, takes place in the outermost energy level containing valence electrons. Second, we can talk about the effect on environmental factors. And we're saying nuclear reactions, they are not affected by environmental factors such as temperature and pressure. But when we're talking about chemical reactions, they are affected by environmental factors such as temperature and also pressure. Remember, we have done that one in the rate of reactions, factors affecting the rate of chemical reactions. So number 3, we talk about the amount of energy released. So we can say the heat released is in large amounts. When we're talking about chemical reactions, the heat released is much less when compared to nuclear reactions. So these are the answers for question number 29, part A, and part B. We are going to proceed to question number 30. Question number 30, we are told state the particle that's responsible for electrical conductivity in solid substances. So the answer is delocalized electrons, or we can write electrons, no problem. So next we are going to question number 31. We are told state any one use of chlorine. We have several uses of chlorine. You can pick any one. Number 1, we can talk about manufacture of hydrochloric acid. Number 2, manufacture of plastics such as polyvinyl chloride or PVC. So learners, we are going to proceed to the answers for question number 30. We are having the localized electrons and also 31. So in 31, we are told state any one use, but we have stated 4. You can pick any one there. Learners, that's the end of our class for today. Thank you for watching.